definition. The work done by a variable force F of x in the direction of motion along the x-axis from x equal to a to x equal to b is equal to the integral of f of x dx from a to b. So like we said, that the units of measure would be in joules if its force is applied in newtons and displaced in x meters, and then if it's the work is equal to foot-pounds if force is applied in terms of pounds and displaced in x feet. So suppose we have a variable force f of x equal to 1 over x squared newtons. And so if you want to find out how much work is done to move the object from 1 meter to 10 meters, then we just apply the, we plug in all the information. So f of x, we substitute there. So you integrate, and the integral of x to the negative 2, remember this is written as x to the negative 2 is equal to x to the negative 1 over negative 1, which makes it negative 1 over x, evaluated from 1 to 10. And you know, this is just all arithmetic, and if you add these two together, that's 0.9 of a joule. All right, now let's just look at a variable force equal to kx, which is Hooke's law for springs. Okay, it says that the force required to hold a stretched or compressed spring x units from its unstressed length. In other words, is when no force is acting upon a spring, so it's in natural length, then the force is proportional to the amount of units that it gets displaced. So F is equal to kx. So F is equal to kx, right, where k is the force constant or spring constant of the spring. Now, in Hooke's law, this equation gives good results as long as the force doesn't, distort the metal in the spring. So here we assume that the forces that we applied will not actually distort it. Okay. Right. So let's see if we can look at a particular problem. And in particular, let's see example 2 from your book. Find the work required to compress a spring from its natural length of 1 foot to a length of 0.75. In other words, you apply force to compress the spring. Like when you push a battery inside, where inside, let's say in a flashlight or something, then you compress the spring. So what is the work done? Find the work required to compress a spring so that it is moved by think about it, from 1 foot to 0.75 means the distance of displacement is 0.25. All right. So here we use this equation. W is equal to the integral of f of x dx from a to b. And f of x is equal to the linear function kx, where k is equal to 16. So it's just a simple integration from 0 to 0.25. Remember, that's the amount of displacement, and it's equal to 16x dx, and that's just using your integration and evaluating it from 0 to 0.25 will give, that's just 8x squared, and when you multiply x squared, when you substitute 0.25 into x squared, you get 8 times 0.0625, and that is equal to 0.5 foot-pound. Okay, so think about it. In some ways, we can look at the work done by the force that is applied on a spring as the area under the curve where the force is equal to this linear function. So the area under the curve is equal to the work done by the force. And see, the displacement is from 0 to 0.25 of a foot. Okay, how about we look at another example? Right here, example 3. A spring has a natural length of 1 meter. So here is the natural length of 1 meter. A force of 24 newtons holds the spring stretched to a total length of 1.8. So think about it. If this is your starting point where this is 1 meter, it got stretched up to 1.8, which means the displacement on the spring is a distance of 0.8 of a meter. Okay, we are to work on A, B, and C. Letter A, find the force constant K. Letter B, how much work will it take to stretch the spring 2 meters beyond its natural strength, which means from 1 meter to 2 meters stretch. Okay, and then letter C, we are to find if we apply a force of 45 newtons, how much x displacement has occurred, or how much stretch has occurred on the spring. All right, so let's see. To find the constant K, we use our equation F equal to Kx, and we just substitute what's given. So 24 units is equal to F, and then it's displaced by a 0.8 of a meter. So we substitute that, and that divide everything by 0.8. We get K is equal to 30. So now our variable force function is equal to 30 times x. Now let's move on to B. And we found that the force constant K is 30. So from A, we know that F is equal to 30x. So how much work will it take to stretch the spring 2 meters beyond its natural length? So the displacement is 2 meters, so we use W is equal to the integral from 0 to 2 of f of x dx, which is 30x dx. And that's just, simple integration. And then you evaluate it from 0 to 2. So 15 times 2 squared is 4. So it's equal to 60 joules. Remember that the unit of measure here is Newton meter, which gives us joules. How about letter C? How far will a 45 Newton force stretch the spring? Okay, so we've already looked at our F equal to 30x. Okay, so our problem now is to find how much was it stretched if you have applied a force of 45 newtons on the spring. So just substitute what's given. F is equal to 45. So 45 equal to 30x. Divide everything by 30. And of course, you reduce that. You get 3/2. So x is equal to 1.5. Which means that if you apply a force of 45 newtons on a spring to stretch it, the displacement will be 1.5 meters. So from its natural length of 1 meter, then it is stretched up to 2.5 meters. All right, let's go to exercises or exercise 6.5, number 1. Spring constant. It took 1,800 joules of work to stretch a spring from its natural length of 2 meters to a length of 5. So what is the displacement that took place? How much distance has it stretched? Well, from 2 to 5, that means 3 meters displacement. Find the spring's force constant. So we've got W is equal to 1,800. And so we want to find K. Remember, our equation is equal to W equal to 0 to 3. That's the displacement. And Kx is the variable force using Hooke's law. And so what we want to do is we want to find K based on what's given. So we plug in all the information that's given. W is equal to 1800. And here we can easily pull out the constant K and just integrate x dx. We get x squared over 2. And then, of course, you evaluate it. Evaluate from 0 to 3, you get K times 9 over 2. And so you just multiply both sides by 2 over 9, and that's what I get, where we got that, to get K. So the constant, or the force constant, K is equal to 400 once you simplify this term. All right, so how do we do number 2? Well, go back to the video and see how example 3 was worked out, and you should be able to solve this problem. Okay.